Okay, so we have some differences to the original study. Yeah, the fact that we're using some sort of grayscale might be a problem. Why are we using grayscale to begin with? I don't know. The data is already pre-processed. All the images are in the same dimension, I'm pretty sure. We should double check and actually not do any pre-processing at this stage. So all the images just rely on the folder names in the current dataset. We don't need to do anything with it at this stage. Yes, so the general structure of the convolutional neural network is similar, but we might have some differences. The original study might have had additional layers, different activation functions, or more filters in the convolutional layers. But we do have the paper. It doesn't mention any of those, so it has the description of what the model design was like. So why can't we just use that? So if we are using that, then why we are not getting the same results? And more of a philosophical question is, if there were other settings, a more complex model architecture was used, why is it not mentioned in the paper? Was the intention for it was for others not to be able to reproduce the results? So can we find all the settings necessary for reproducing the model in the paper itself? Yeah, we have a description of the dataset. We have the images from the paper. So if we have a different optimizer or hyperparameters, yeah, we need to dive deep, see what's different. We're still trying to replicate the original results. Potentially we might later just try and improve the model. So we'll have essentially two separate training algorithms. One as close as possible to the description in the original paper, and another one which is actually like optimized based on the current dataset structure. Now the original study might have used a different training schedule, including more epochs, a different learning rate schedule, or additional regularization techniques like dropout in specific layers. If we could extract all the details from the study and replicate it in our code, that will be great. If any of it is not mentioned in the study, we need to know about it. Can you check and let me know what's actually missing from the description in the original study? So the original paper reported results on a separate test set. Do we have it? Might not have it. The test accuracy reported at 61%. Anyway, we can't essentially reach anywhere above 50%. So that's doesn't sound promising, does it? Can you also in one sentence just mention the results from the original paper, just so we keep it in mind while doing this?
Let's break down your queries and the approach to align the current model more closely with the original study while also addressing your concerns. Grayscale conversion and image preprocessing. In the current code, the images are converted to grayscale, which might not be necessary if the original dataset was already preprocessed and formatted as required by the study. The grayscale conversion reduces the image's color information to a single channel, which could strip away useful features that the original study might have used if they worked with color images. If the images are already pre-processed and standardized in size and format in the dataset, it would indeed be more appropriate not to alter them further during training. You can skip the grayscale conversion and simply load the images as they are to maintain consistency with the dataset used in the original study. CNN architecture and differences in the study. The CNN architecture in your current code is relatively straightforward. If the original study's architecture is clearly described, you should replicate it exactly to avoid discrepancies. From your description, it sounds like the original paper does mention the architecture, but lacks detailed information about specific training settings, such as the optimizer or learning rate schedules. This absence might contribute to the differences in the results. If the study doesn't specify certain hyperparameters or training settings, it's possible the authors used default values or settings that they didn't document, which might lead to reproducibility issues. However, this isn't necessarily done to obscure replication. Sometimes certain details are overlooked or assumed to be common knowledge in the field. Reproducing the original study. To faithfully reproduce the original results, 1. Ensure all image preprocessing matches. Skip unnecessary preprocessing, like grayscale conversion, if the images are already in the required format. 2. Match the CNN architecture exactly. Replicate the architecture as described in the study. This includes the number of layers, filter sizes, activation functions, and pooling layers. 3. Use identical hyperparameters. Use the optimizer, learning rate, batch size, and epoch count exactly as mentioned. If these are not specified, start with common defaults used in similar studies. 4. Training schedule and regularization. If the study doesn't mention techniques like dropout or specific learning rate schedules, it's safe to assume they were either not used or the default settings were applied. Missing information in the study. After examining the provided images and text from the study, here's what might be missing. 1. Specific hyperparameters. The study might not mention the exact learning rate decay, momentum, or other hyperparameter settings used during training. 2. Data augmentation techniques. While some techniques might be mentioned, the exact parameters for augmentation, e.g. how much rotation, shift, etc., might not be detailed. 3. Optimizer details. The exact configuration of the optimizer, e.g., any special settings or modifications, might not be thoroughly explained. Performance results. According to the details you provided earlier, the original study reported a test accuracy of 61%. Your model, which is currently achieving around 50% accuracy, shows that it's performing at the level of random chance. This suggests that there's still work to be done in either aligning the model closely with the original or improving it for your current dataset. Next steps. 1. Cross-check and adjust. Go through the study and make sure every possible detail of the model's architecture, preprocessing, and training regimen is replicated as described. 2. Simplify the preprocessing. Remove unnecessary steps like grayscale conversion if the images are already prepared. 3. Test different configurations. If you're still not achieving the expected accuracy, consider testing different hyperparameter configurations or even a different architecture to see if the performance improves. If you can implement these changes and continue testing, it should help you get closer to the results reported in the original study.
Okay, so skipping the grayscale conversion and other preprocessing that we currently have in the code is a great idea. Yeah, I want to maintain consistency. I think the dataset is already pre-processed. Yeah, we would like to double check in the paper or the dataset description. I'll just pull it up next as well. I added the table from the study that actually has all the model configurations and the results. Yeah, if you can go over that would be great.
Let's go through the important details from the original study's model configuration and the dataset information to align your implementation with the original setup. Model configuration and results from the original study. In the original study, the model configuration is as follows. Epochs, 15, batch size, 16, optimizer, stochastic gradient descent, SGD. Learning rate, 0.01, decay, 1e6, momentum, 0.9. The model achieved the following performance. Average accuracy, 91.89%. Average validation accuracy, 88.17%. Average training loss, 0.244. Average validation loss, 0.1819. Training time per epoch, 14 seconds. Model size, 8.93 megabytes, H5 file. Hashtag dataset details. The dataset is pre-processed and divided into the following sets. Training set, 240 seizure images and 240 non-seizure images. Validation set, 30 seizure images and 30 non-seizure images. Test set, 30 seizure images and 30 non-seizure images. Each image is likely to have been pre-processed before being added to the dataset. Therefore, applying additional preprocessing like grayscale conversion may not be necessary or could even negatively affect the model's performance. It's important to use the images as they are, especially since the original study likely worked with preprocessed data. Steps to align your implementation. 1. Skip grayscale conversion. Ensure that the images are used in their original color format instead of converting them to grayscale, as this aligns with the dataset used in the original study. 2. Model architecture. The architecture used in your current implementation is generally similar to that in the original study. However, to match the exact results, confirm that the activation functions, number of filters, and layers match those described in the paper. This paper doesn't explicitly mention these details, so ensuring they align is crucial. Hyperparameters. Ensure you match the hyperparameters exactly, especially the learning rate, decay, and momentum values. 4. Test set accuracy. The original paper reported a 61% test accuracy. Your implementation is currently below this mark, which suggests that tweaking the model to align more closely with the original setup, e.g. no preprocessing and exact hyperparameters, might improve performance. Summary. To replicate the results from the original study, avoid additional preprocessing like grayscale conversion. Match the model's architecture and hyperparameters exactly as described. Focus on using the preprocessed dataset directly without modifications. By aligning your implementation with these details, you should be able to achieve results closer to those reported in the original study.
So I have 600 files all up in 9 folders. Yeah, we have 3 types of datasets: train, test, validation, and each has seizure and non-seizure folder in it. The train dataset should have 240 images for each seizure and non-seizure types. And above is the structure of the whole dataset.